forces exerted on the positive charges that are free to move inside the body of metal of the ring into the plane of the board at the bottom, and out of the plane of the board at the top. So now the current will flow in the opposing direction, and that will create a magnetic field that is oriented in the opposing direction. So as you bring this ring of metal in toward the magnet, okay, it becomes the side of the ring closest to the north pole of the permanent magnet becomes the north pole itself, and there's a repulsive force. As you pull it away, it becomes a south pole, and there's an attractive force. So there's a resistance to the motion in both cases. Why? Well, because it requires force through a distance or work or energy to create current. Okay? So that comes from that resistance. Does that make sense? Interesting, huh? So the motion of this magnet with respect to this ring induces a current to flow in the ring, which induces a magnetic field. Any questions? Okay. He did all kinds of experiments. He did it with different sized rings. Okay? Different sized rings created different amounts of current. He tried it at angles. He tried rotating the rings. Everything. What he eventually found that it had to do with the strength of the magnetic field and the area that the magnetic field had to pass through. In other words, the area of the ring enclosed by the ring. The angle between the plane of the ring and the magnetic field, and how fast those things were changing. Okay? If you bring it in really fast, you're changing the strength of the magnetic field seen by the ring really fast, right? Because you're getting closer, it's getting stronger and stronger and stronger. So he introduced something. He said, and I already introduced the idea of magnetic flux. I know I've done it for electric flux. Did I talk about magnetic flux yet? Okay. Okay. And what are the units for magnetic flux? Yeah. But it's given a special name. The 1 level. It's abbreviated to capital W, lowercase p, and it's equal to 1 Tesla of magnetic field passing through the area of 1 square meter. So, Faraday's law goes like this. he said it's not just that there's an induced current. Hey, if there's a current, it's being driven by a voltage. So there's an induced voltage or an induced EMF. Okay? And the equation looks like this. The magnetic flux through a closed area or through a closed loop. Is equal to 0. Now this one I already told you. Okay, that's not Ampere's law. That's not Faraday's law. This is Faraday's law. Hadn't I already shown you this one? I think so. When we first talked about magnets, remember, if you've got a closed area, a completely closed shell, the magnetic flux in has got to be equal to the magnetic flux out, right? And that's because there's no such thing as a north pole all by itself or a south pole all by itself. They always come in pairs, so that means that the magnetic field lines circulate. And since they circulate, there's no beginning, there's no end, so there's no way that a closed surface can have a net magnetic flux out of it for you. Right? That's not Gauss's law. That's not Faraday's law. This is Faraday's law. What this says is that a changing magnetic flux, that changes with time, necessarily creates a circulating electric field. That's what a voltage is. Okay? There must be an electric field around that loop, otherwise the charges wouldn't accelerate. They have to have an electric field to accelerate. Right? That's what this says. A changing magnetic flux with respect to time through a closed path will create a circulating electric field around it. So, let's say we've got an aluminum window frame in your house. Okay? And there's a truck filled with magnets going through the magnet, going away from the magnet stack. So it backs into your driveway. Okay, guys, lost. Okay. And as he backs into the driveway, this big magnet in the back of the truck. Okay. Is coming towards your window. It's a metal window. Right? You like sports, right? Okay. What's that going to do? It's going to make a current flow around the aluminum frame of your window. Okay, it'll flow in one direction. As he backs in, as he pulls out, it's going to flow in the opposite direction. There's a changing magnetic flux through the area of this window. That induces a current which was induced by a circulating electric field. Yeah? Okay. So that's Faraday's law. Why the negative sign? What's that? Say again? Because he was wrong. I want you to stand outside.
You said he was wrong.
I'll go stand out
Yes, the most.
The negative sign is there because of something called Lenz's law.
Was he wrong?
Lenz might be able to correct everything. Now here's the deal. Okay, think about this. As you bring this in, this permanent magnet closer and closer to this ring, what happens to the magnetic flux enclosed by the ring? Does it go up or does it go down in the string? Up or down? Yeah, it's stronger and stronger, right? Stronger magnetic field area is the same. So B times A, which is basically the magnetic flux, gets bigger, right? In what direction does it get bigger? Like that way. Okay. Yeah, you agree with it? Okay. Now, the magnetic flux induced is going to what? It's going to get bigger too, right? But in what direction does it point? In the opposing direction. Okay? The negative sign tells you that it's all, the induced magnetic flux is always opposite direction of the magnetic flux that created the induced flux. So here you've got a permanent magnet coming in, creating larger and larger magnetic flux in the area enclosed by the ring. The ring has a current set up in it that circulates in such a way that it creates its own magnetic flux in the opposing direction. Okay, so Lenz's law says that the induced magnetic field will always counter the change in the external magnetic field. That counter is where the negative sign comes from. Okay? Now, if you pull the ring away, then what happens to the strength of the external magnetic flux with respect to the ring? Does it get stronger or weaker? Weaker, right, it goes down, okay? So, what direction is the external magnetic field? This way. So, as you pull the ring out, remember the direction of the induced magnetic field becomes opposite, okay? So, since the magnetic field, the external magnetic field, is decreasing in this direction, imagine the field getting shorter and shorter and shorter due to this ring as you pull this ring further and further away. It has to counter that change by creating a magnetic field of its own in that direction. So the induced magnetic field will always counter the change in the external magnetic field. That's Lenz's law, and that's why there's a negative sign in front of the right-hand side of Faraday's law. He was right. That's on the next list. Was Faraday right? Okay. So, no. Well.
I ate too much candy.
Spicy.
So bad. No.
No, it's not. You know what it is?
Brain pop.
If it had a battery in it, it'd be a railgun. It doesn't have a battery in it. You know what it is?
Not a brain pop.
It's the simplest electrical generator ever. Here's a resistor connecting two metal rails. And on top of that, those rails is a metal bar that's in between the two of them. And let's say we've got magnetic field that's pointed in this direction. Say it's constant. And let's say we've got a little rope Okay, you're pulling it this way. Um, okay, so what's that gonna do?
He's gonna pull in the bar.
Gonna pull that bar. Is that going to do anything that we might have spoken about recently? It'll induce a current. Okay, smart guy. What direction will the current flow? In the bar, will it flow out of the board or into the board? Out of the board or in the board? Out of the board. Out of the board? You got a 50-50 shot at this. So, okay, so index finger points up, because that's the direction of the magnetic field. All the charges that are free to move in the bar, moving in the direction the bar is initially, so your thumb points. So the force is exerted on those would be very good. Out of the board. So I flows in this direction. I. And that would mean that it's going this way and up through this resistor. Back. Right? Now, well, let's say that you are pulling this with a speed v. So v is the speed that you're pulling this. Okay, and it's a constant. Now, let's say that this distance is x. X is going to be changing with time, isn't it? This distance between the far end of the rails where the end that you got a resistor connected between and the bar, that's going to be changing continually because you're pulling this with a constant speed v. Do you agree with that? Yes? Okay. Well, the magnetic flux here is equal to V dot dA, right? And in this case, V is directly upward. A is a vector that points perpendicular off the surface enclosed by the sliding bar, the two rails, and the resistor. So it's a rectangular area, right? It's this area here, that's area A. And let's say that the distance between the rails, let's call that L. So that's also the length of the bar here. So the magnetic field is oriented this way. The dA vector is oriented in the same direction. So the dot product of that is just going to be magnitude of V, magnitude of dA times cosine of 0 degrees, which is just 1. So this can be written as V times A. Good. So that's the magnetic flux. Is the magnetic flux changing with time? Because Faraday's law, that's the important part. You want it to change with time. Yes? Why yes?
Because you're pulling.
The magnetic field is not changing with time. What's that? The area is, right. Okay. The length. So what is the area? What's the area in terms of variables I've got up here? X times L, right? Okay. So this could be written as V times L times X. Agree? That will be the flux, the magnetic flux enclosed by this system at any point in time. Good. Now, over here, the important part, the important thing to do is be able to take the integral, the derivative of the magnetic flux. So if we take the partial Is magnetic field changing with time? No. Is L the length of the bar changing with time? No. Is X changing with time? Yes. So if we do this, we can bring B and L outside and just do, just call it more kind of ordinary derivative of X with respect to time, right? But what is another name for dx dt? Velocity, v. So that means that the time rate of change of the magnetic flux for this particular system is just v L v little v. So little v is the velocity that you're pulling this bar with. Good. And that, my friends, is equal to the electromotive force. Okay, same thing as a voltage. Remember this? Remember one of the ways we learned to express the units of the electric field? One of them was newtons per coulomb. What was the other one? Newtons per coulomb or volts per meter. Okay? So here the units are volts per meter. What are the units for DL? Meters. So a volt per meter times a meter is a volt. This is voltage. This is like the driving voltage of the circuit. Okay? So that's what this is. And by the way, we're only concerned with the magnitude of this. I'm not going to worry about the negative sign right now. We already figured out the direction of the current. That's really what the negative sign is about. Okay? So if that's the voltage, and you've got a resistance, what is Ohm's law? V is equal to, yeah, so this can also be set as I times R, right? When we divide through by R, we've got the current to be equal to the magnetic field times the length of the bar times how fast you move it through the field divided by the resistance. And that's the current in our electrical generator. A stupid, simple electrical generator. Okay? What does an electrical generator do? It takes mechanical motion or mechanical energy and converts it into electrical energy, right? And that's what we've got here in its simplest form. Okay, good. What else can I tell you about that? Well, do you remember the power equation? Let's say that's effective. Let's say this isn't just a resistor. Let's say it's a light bulb. Okay? That's a light bulb, so it lights when you pull the bar through the magnetic field. You created a current that's going through the filament. So, good? Okay. Can you calculate the power of that? What is the power equation for electrical or for circuits that yeah, I squared R. Okay, so here's I. So the power, the electrical power, is I squared times R. That's going to be V squared L squared V squared over this R, because it's R squared, but then you multiply by R. So this is the power output of our electrical generator. Make sense? Now I said there was no resistance between the rails and the sliding bar, right? And I also said that you're pulling on this thing and it's moving at a constant speed. Right? Didn't I say all that? Is he okay? Hello? And I told you that this thing has a current flowing through it, right? And remember, I think the first equation in magnetism is this Q V cross B. Okay, so that's for a charge moving through an external magnetic field. But then we've changed it. It can also be written like this, I L cross B. Right? Okay, where this vector L is in the direction of the wire or R, whatever, that's moving through the field in the direction the current is flowing through it. So that's out of the board, I, and then cross B, okay? Your thumb points in the direction of the resulting vector, which is opposite. So it's a drag force. So as you pull this thing through the field, current begins to flow through it. That current, that moving charge interacts with the field, creating a force that is a drag force. Okay? So if you're pulling this with a constant speed, then that must mean that the force that you apply, F applied, must be equal to this force. And this force, the magnitude of it, is just I, L, V. Agreed? Okay, well, we found out I is equal to this. So we can write this as, oh, by the way, this force must be equal to the force that you apply, since you're moving at a constant speed. So that's got to be equal to I times L times V. There's I, that's going to be V squared, L squared, V over R. Right? Now, what power do you have to put in? In other words, what is the applied power, the mechanical power? Well, that's the force dotted with the velocity, right? Or just F applied times V. Well, here's F applied, so the applied power is going to be equal to V squared L squared V times V, V squared over R. So that's the power that the mechanical input has to have. Yeah.
Down there is not useful.
Down where?
Where you at? Where you at, what's the plus?
No, it's not. No, it's ILV, right? And I is equal to this. So V is not squared here. Okay? So notice that this and this are identical, right? So the energy that you put in per unit time, on the mechanical side, if you're doing mechanical work, has been completely converted into electrical energy per unit time, 100% efficiency. Okay? An electrical generator quite typically can be over 90% efficient. Electrical generators are some of the most, and electrical motors are some of the most efficient devices ever. And that's one of the reasons that some people think that electrical motors will eventually be the way that, you know, every type of transit is done. Heat engines are notoriously inefficient, you know, even theoretically, maximum theoretical efficiency of a heat engine, like basically us, we're heat engines, okay? We have to metabolize food. We're basically slow burning it, right? And we have to heat up our systems, and we're typically maybe only 30% efficient at converting, you know, the food energy into useful work. And 30% efficiency is like the theoretical max that you can have for internal combustion engine. But electrical motors and electrical generators are typically extremely efficient. Okay, so that's an example of the use of Faraday's law. this work led him to create the first motor, and led other people to really capitalize on those ideas and create motors that were really very, very useful in electric motors by the end of the 1900s. He created the first electric motor in 1837, and 50 years later, there are electric motors everywhere. And now, they're, a big part of modern technology. Okay. What is this distance called right here? Out to the near part of the loop?
A.
That's A, and then it's B to the far part of the loop?
Yeah.
Okay, that's B, and then do they give you this dimension?
L.
Okay,
And then in the middle, there's a little line.
yeah, okay, so I'm gonna draw that with a different color. But, okay, we got this rectangular loop over here, close to this wire that's carrying current up the board, but that current is getting greater and greater with time. Didn't you say that the IDT was constant?
No. DIDT is increasing steadily at a rate.
Okay, so DIDT is equal to C times T. Some constant times time. So it's increasing at a steady rate. Okay, where C would be greater than 0. That makes sense because it's increasing. Good? Oh, wait. No, DIDT is not increasing. I is increasing, right?
No, AB, is increasing. The
So
current,
I is equal to C times T. So DIDT is just some constant. That's what it's saying.
yeah.
Okay. So in here we've got this region, just a little pretty region. Distance out to this is R, right?
Yeah.
Okay. And the thickness of this is just D. So this is a little bit of area here. And the area of that is going to be L times dr. And that's dA. That make sense?
Yep.
Okay. And we wanted to find the magnetic field due to the long straight wire at some time when the current is I, right? And that's just V is equal to mu sub 0 I divided by 2 pi R. That's an equation that we learned how to derive last chapter. Is that the first part?
Yeah.
Okay. What's the second part?
Okay. What is the flux D flux B through the narrow shaded strip?
Okay, so what's the flux through there? What's the flux? B is, or P sub B is equal to V times dA. That's a small amount of total flux, dP sub B, and it's equal to the magnetic field in that region times the area. We just figured out the area to be L times dr. So we can write that as mu sub 0 I L dr. All of that divided by 2 pi r. So that will be the flux through that little shaded area.
The rate C. Okay. What is the total flux through the loop?
Okay, so the total flux through this loop, how do we get that? Must be an integral. So what we have to do is add up the flux due to all of these little pieces that are L long but dr wide, from A to B, right? So that total flux, B sub B, will be equal to the integral of all the little dP sub B's. And that's going to be equal to this thing. So mu sub 0 comes outside. right? And if we do that, it's gonna be natural log of P over A. So we end up with use of 0 I L divided by 2 pi. All of that times the natural log of B over A. So that'll be the total flux through that rectangular loop. Do you agree with that? Okay, now what?
What is the induced EMF in the loop?
The induced EMF is equal to the negative of the time rate of change of the magnetic flux. Here's the magnetic flux. The time rate of change of the magnetic flux, well, everything here is a constant except for I. So just replace that with dI dt, and you're done, basically. So, the induced electromotive force will be use of 0 L natural log of B over A all divided by 2 pi times dI dt. And that's the magnitude of it. Okay? Is that the whole thing?
No. Evaluate the numerical value of the induced EMF at A equals 12 centimeters, B equals 36 centimeters, L equals 24 centimeters, and dI over dt equals 9.6 amps per second.
Okay, so I'll let you do that work. You just plug in the dice. Okay. Good. Does that make sense to everybody?
B was 36 centimeters.
So. Can we do 56? They've got problems associated with it. They've got terminal speeds. There's only so fast that slug can go. And you can find out. Okay. So, so go ahead and read that one.
Bar of length L equals 0.36 meters is free to slide without friction on horizontal rails and blah blah blah. The uniform magnetic field E equals 2.4 Tesla is directed into the plane of the figure at one end of the rails there is a battery. EMF E was 12 volts and switch S.
Wait a minute, okay, so V sub S is 12 volts.
The bar has mass 0.9 kilograms, resistance 5 ohms. Ignore all other resistance in the circuit. The switch is closed at time equals 0. For part A, sketch the bar's speed as a function of time.
Okay, so, first of all, I'm drawing now. Here's VS. Here's the rails. Here's the bar. Real gems look really cool. Which direction is the magnetic field, into or out of the page? Into. So here, 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 here. Okay, now, since there's a current, there will be a current, due to this, is there a resistor in here too?
No, this is the bar.
Oh, that's right, the bar has resistance, so there's a switch though. You close the switch, current flows, and if current flows down through this bar, L cross B gives you the magnetic force this way, which it should be, right? You don't want it to run back and hit the person who closed the switch. So it's pushed that way, right? Okay, and that's equal to I, L, V, and that's gonna be I for the battery is equal to, VS over R, right? Ohm's law. So that's gonna be, V, L, VS over R. That'll be the force exerted, due to the current flowing through the magnetic field, right, and the direction. And we wanted to sketch the velocity. Well, here's the problem. As that thing moves to the right, x, the distance between the left-hand end of this system and the bar, gets bigger and bigger, right? So that means the area gets bigger here, and that means the magnetic flux is changing with time, right? So the induced electromotive force will be, the magnitude of it, which is what we're concerned with, will be equal to the time rate of change of the magnetic flux. And that's going to be equal to V times L times dx dt, which is equal to V, L, V, where little v is velocity. Good. In what direction will that take place? Well, remember Lenz's law. Well, first of all, before we do that, think about the charges that are free to move in this bar. Okay? Before this turn. If the bar is moving this way, then all the charges that are free to move in the bar are also moving in that direction, right? The magnetic field, which is denoted by the direction your index finger points, is into the board. So the force exerted on those charges due to the changing flux is upward. So that means I induced is in the upward direction. So my guess is that eventually the velocity is going to be big enough that the induced current will exactly counter the current of the battery, at which point you're going to have zero current, right? And at which point you've reached terminal velocity. Okay? So, and what about the force? If there's an induced current in this direction, L cross V gives you an induced force in this direction. So there's a drag force acting on this system. Okay? So you've got the forward force due to the battery, and you've got the reverse force due to the induced EMF, due to Faraday's law. So there's a drag force acting on this slug that's trying to move down the barrel of your rail. Okay, so E induced is equal to V, L, V. Yeah, and that's also equal to I induced times R. So I induced is equal to V, L, V over R. Yeah, and the force, the induced force, is equal to I, L, I induced, L cross V, or just I induced, L V. Here's I induced, so the force induced is equal to V squared, L squared, V over R. So, you've got a forward force due to the battery equal to this. You've got a reverse force due to the Faraday's law equal to this. seen that equation? Okay. Well, I don't think I taught my physics one student system. I just skipped over anything to do with it.
He's always wrong.
So this force minus this force should be equal to mass times acceleration. So that's going to be V L ds over long minus v squared L squared little v over r is equal to m times dv dt. Because dv dt is like acceleration. So I'm going to divide through by m, multiply by t, divide through by everything, and something like that. Let's see here, we'll have, dt will be equal to dv divided by L ds over mr minus b squared L squared little b over mr. Now I'm going to integrate both sides of that because now I've isolated everything with b on one side of the equation. And if I integrate this from, say, time equals 0 to some arbitrary time t, over here I'm going to integrate from velocity equals 0 to the corresponding time at our velocity v. Then I'll have integral dt from 0 to t, which is just equal to t, is equal to, let's see, the integral from 0 to some arbitrary value v, dv over the quantity v L ds over mr minus v squared L squared little v over mr. Okay, now that's going to be some kind of a natural law of something or other, right? So you make everything here, I would call that, what is that, hashtag? What is it? Pound sign? What is a hashtag? The same thing? Okay, so, is that right? That's right, isn't it? So, going to be equal to, what we want is dv. dv is going to be equal to negative mr over b squared L squared. Good. So we can take this, plug it in right there, and if we do that, we're going to get something just like negative mr over b squared L squared integral the hashtag over hashtag. Okay. Right? And so now we're integrating with respect to this, where over here we were integrating with respect to v. So if our limit was v, if we plug that in right there, we just get v L ds over mr. And up top, we're going to get this whole thing. Wow. Right? Okay, so this is going to be equal to negative mr over b squared L squared natural log of so the first term is gonna be one, because here's the first term divided by this, right? And then the next term, let's see, this over this. What's gonna be left? Just a B, L, V. Isn't that right? You tell me. Is that right?
You're the math.
Whiz.
You're going fast.
Oh. Well, I did separation of variables, right? And then I had to do a use of. Does that look right? Now, okay, so t is equal to this. So I'm going to take all this stuff, multiply the denominator, divide through by that stuff, and I end up with negative b squared l squared t, and divide that by mr. And that's going to be equal to the natural log of 1 minus bl v over bx. Now, I don't like the
Hashtag.
logarithmic form, so I convert to the exponent form because I want to solve for the velocity, right? So, and it's an argument of log. So, e to the negative b squared l squared t divided by mr is going to be equal to 1 minus b l little v over dx. Yeah. So I'm going to take this term, add it over here, subtract this term, multiply by dx, divide by bl, and I'll isolate the velocity of time. So that should be the velocity. Is it? I think it is. Yeah, it is. This right here is the terminal speed. Okay? Think about it this way. If you were to graph this, what kind of function would you get? Well, if t equals infinity, e raised to the negative infinity is 0, right? So a long time after the switch is closed, this term goes away. So this is the remaining term. This must be the terminal speed. What is the speed at time equals 0? Time equals 0, e raised to 0 is 1. 1 minus 1 is 0. Should be. So that works. If you were to graph this function, it's going to look like this. Here's time, here's velocity, here's the horizontal asymptote at vs over dl. And it starts at 0 and it approaches that. That's the graph. Now, what was Vs again? Was it 12 volts? So 12 volts, what is the length? 0.9 kilogram? Or no, I'm sorry, point. So somebody do this. 2.4 times 0.36. So what is 12 divided by 0.864? So that should be the terminal speed. So D terminal was 13 what? 0.9 meters per second. And that's this right here. Okay? So that's the part A. I think it gets harder. What was the rest of that?
Part B, just after the switch is closed, what is the acceleration of the bar?
What is the what?
Acceleration of the bar.
The acceleration, well, here's velocity. dv dt will be the acceleration. So, the acceleration, function of time. Okay, there's two terms here. First term is going to be 0 when you take the derivative. Second term, negative, that's going to go away. D squared, L squared, over mr that's the velocity at all points in time. The velocity at time equals 0. Time equals 0, e raised to 0 is 1. So it's going to be dl ds over mr. So somebody do that. dl ds. So multiply all these together, then divide by these two multiplied together. And tell me what you get for the acceleration. Two point three meters per second squared. So that's the initial acceleration. And it just gets smaller and smaller and eventually reaches 0 when the terminal speed is 0. More?
Let's see, what is the acceleration of the bar when the speed is 2 meters per second?
Okay. 2 meters per second? Okay, so what you do is you set this side equal to 2. This right here is 13.9. Solve for the value of time that makes that true. And then you'll find the time, and then you take that value of time and you plug it in right here. And remember, this part is equal to 2.3 meters per second squared. That'll give you the acceleration at the time when the velocity is 2 meters per second. Does that make sense? Was there more?
What is the bar's terminal speed?
13.9 meters per second. Was that it? Okay. So, that's that one.
I'm like, real one.
That's, but, you know,
Enormous.
hey, the moral to this story is, if you want to make a railgun that's got a speed greater than 13.9 meters per second, which is pretty slow, like, 20 miles an hour, 25 miles an hour, you want to use more than just one car battery. Okay. More than one 12-volt car battery. So, and if that was a little too fast, I'm sorry, but I didn't know how to slow it down and get done in a short 40 Okay. I had a wonderful, stimulating, fantastic. What time? What's it? Okay, y'all. We got to do some problems. And